Hi everyone, in today's video we're going to be following up the work that you did in Desmos and talking a little bit more about how we find the instantaneous rate of change, or what we now know is the slope of that tangent line. So our big idea here was how to write the equation of a tangent line, because we know that requires us to find the slope of a function at one point. And so prior to now we didn't really have a way of finding that equation. So, just to fill in a few things here to get us all on the same page, we know that the slope of the tangent line is called the instantaneous rate of change. And just as a side note, I'm going to make myself a note here. We know that's the slope of the tangent line. We knew before that the slope of the secant line was the average rate of change. And I just want to keep bringing that up because you'll kind of hear these terms used interchangeably. So the slope of the tangent line is the instantaneous rate of change, and the slope of the secant line is the average rate of change. Now, as we go forward, we're going to be using another name and some new notation for that slope of the tangent line, and we're going to call that the derivative. And along with that derivative comes a whole bunch of new notation that you're going to get to be really familiar with. So when we see notation that looks like this, dy dx, we might see what we call y prime. That tick mark there is going to represent that derivative. You might see f prime of x, which would be the derivative of the function f of x. And then you might see something like this, the derivative with respect to x of the function f of x. And so right now what we need to know is the slope of the tangent line, the instantaneous rate of change, and the derivative are all different names for the same thing. And this is notation that's going to tell us we're looking for a derivative. Now, what we talked about in Desmos was actually how do we find that slope of the function since we only have it at one point. And we're going to learn a few formulas here, and each one is going to kind of be specific to a certain type of scenario. Now, our first option is when we know the specific value at which we want to find the slope. So we're finding the slope at a specific value. Now here's what that formula is going to look like. The formula is going to be the limit as x approaches a of f of x minus f of a over x minus a. Now graphically, here's kind of what we're looking at. Let's see if I can draw this here. Let's take something that looks like this. Say this is my curve, and I'm going to do this. Let's see, let's call this A and this X. So then I know if I go up here, I have the value f of A, and I have the value f of x there. And so what we're representing here, this f of x minus f of a over x minus a, hopefully that looks familiar to you. That's just the slope between our 2 points. That should look like when we were calculating that average rate of change. But now if we think back to Desmos, right, if I were to make x approach a, so in other words, if x were to get closer and closer in A, that's like in Desmos where we're sliding those points together. This limit slides the points together. And what we saw in Desmos was that as we slid those points together, that secant line, the slope of the secant line, got closer and closer to the slope of the tangent line. So the slope of the secant line I could represent like this. But we said as I slid x closer and closer to a, we would get closer and closer to that slope of the tangent line at x equals a. So that's kind of visually what we're trying to illustrate here. So now, what would this look like in an actual problem? So here it says let f of x equals 1/2 x squared, and it wants us to write an expression using limits that could be used to find f prime of 2. So now in this case, that 2 is that specific value that we were talking about. Right? That's our value, what we called a here. So here's what we would do in this case. We're going to use this formula. The limit is x approaches a of f of x minus f of a over x minus a. Now in this case, our a is this value of 2, and our f of x we can fill in with our function 1/2 x squared. So now I'm going to rearrange my camera so you can see this. Sorry about the jump. Now if I make those substitutions, I've got the limit as x approaches, we said our a was 2, of our function 1/2 x squared. Now, again, we said this a was 2, so this is really equal to f of 2. So I'm going to plug in f of 2. If I plug in 2 to my function, 2 squared is 4, divided by 2 is 2. So I get 1/2 x squared minus 2 over, and then I've got x minus, and again, our a value was 2. So this would be an expression using limits that would help us find f prime of 2. Now again, what that would tell us, if we evaluated this limit, and we're not going to right now, but if we evaluated this limit, this numeric value would tell me the slope of the tangent line to my function f of x at x equals 2. Now the reason we're not actually going to go through and evaluate this limit is because most times when it comes to the AP exam, they just need you to be able to recognize that this is the derivative. They're not going to have you evaluate this limit. Okay, let's move on to our next option. Now, option 2 is going to be best when we want to develop a general formula that can be used to find any derivative that we want. So opposed to finding it as a specific value, we want to find any derivative. And here's what this formula is going to look like. This one says the limit as h approaches 0 of f of x plus h minus f of x all over h. That's going to be our formula that's going to give us any derivative, or what we call the general derivative. Now again, just to kind of remind us of what we're looking at here, let's think about it if we're looking at a graph. So I'm going to draw my kind of generic graph here. And let's say now I have my point x. Let's say it's x here, and so I know I've got f of x. And let's pick another point. I'm going to call it x plus h. So this value is x plus h. So what I know is the distance between those 2 points is h. And so here I have f of x plus h. So even though it doesn't look like it, this is still the slope of that secant line. I have my y values, f of x plus h minus f of x. On the bottom I have x plus h minus x, which is just h. So that's the slope formula really kind of in disguise there, or what we call, you've probably seen this in calculus, or excuse me, pre-calc, what we call the difference quotient. But it's still that same kind of idea about finding that slope of our secant line. Now here, in this case, we're talking about h approaching 0. So in other words, as this x plus h approaches x, h is approaching 0. So again, this part is what's sliding the points together. So same idea, different notation. And again, the idea being as this point moves closer and closer to this one, I'm going to more closely approximate that slope of the tangent line. So now how is this going to look? Here's our problem, and the setup is very much the same. It says let f of x equal 1/2 x squared, then asks us to write an expression using the limits that could be used to find, f prime of x. Notice there's no specific value there. We just are trying to find the general derivative. So again, just like before, let's kind of work with this and see how this would look. So in this case, I know it's the limit. I'm just going to write the formula down so we get used to writing this. F of x plus h minus f of x all over h. Now let's see what we have for our function. We have the limit as h approaches 0. Now this tells me to take this x plus h, and wherever I see x in my original function, I'm going to replace it with x plus h. So this becomes actually now 1/2. Instead of the x, I have x plus h, and then I still have the quantity squared. Now I'm going to subtract my function f of x, so minus 1/2 x squared, and then this is all over h. That expression would give me, if we were to evaluate that, a general derivative. And again, I know I'm repeating myself here, but remember, this derivative, it would just be giving us a formula to find the slope of the tangent line to this curve at any point that I wanted. Okay, one more option here. Now, it looks the same as where we started. It's best when we want to know the specific value again at which you want to find the slope. But this time, even though we're finding the specific value, we're going to use the formula we used above, and we're going to add a little twist to it. So we're still doing the limit if h approaches 0 of f of x plus h minus f of x all over h. But now when we go to use this, instead of just using a general x, we're going to be plugging in our specific value. So again, I see in the notation here that I'm looking for a specific value. So I always start out by just writing my general formula. So the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, a couple of things are going to happen here. Wherever I see my x, this is going to become the 2, because that was my specific value of x. So now when I go to plug this in, what I really have is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Sorry about that. And so now I'm going to do what I can with this. Now I have the limit as h approaches 0. This f of 2 plus h says wherever I used to have an x, substitute 2 plus h. So this turns into 1/2 times the quantity 2 plus h squared minus f of 2. This is just evaluating the function when x is equal to 2. So that gives me 2 all over h. And so this expression, again, would help me find f prime of 2, or the slope of the tangent line to this curve when x is equal to 2. Now, we are going to be practicing with this a lot over the next couple days. So for now, it's probably important just to be familiar with these 3 different forms. And then, like I said, the mechanics of actually working with it we'll get into a lot more. So thank you for hanging in there, and I will see you back in class.